So welcome to today's lecture on Zener Diodes. Before moving on to Zener Diodes, let us revise the basics of diode. So we know the symbol of diode is something like this, where this lead denotes the cathode, or you can say the negative electrode, while this side denotes the anode or the positive terminal. So this is the symbolic representation of a diode. Now let us draw the PN junctions. So P will be the anode side and N will be the cathode side, and there will be a depletion region between them. Now in this depletion region, we have N-type material towards the P side and P side towards the N side. What does this mean is, suppose there is a depletion region and this is the P-type semiconductor and this is the N-type semiconductor. We know N-type semiconductor contains electrons while P-type contains holes. So electrons will cross over and holes will cross over, and this creates a potential barrier. Which is for silicon 0.7 volts and for germanium it is 0.3 volts. So basically this is what a diode is. Now an important characteristic of diode is the IV characteristics of diode. Let us plot the PI characteristics of a diode. On the y-axis we will be having current, which will be in the range of milliamperes, and on the x-axis we will be having volt. Okay, now as we can see here, silicon 0.7 volt is the barrier potential, so we'll plot 0.7 here. So what happens is, in the forward bias the characteristics will be similar to this. Okay, till 0.7 the current will be low, and then once it crosses the potential barrier the current will rise steeply. In the reverse side, what happens is there will be a small saturation current, and then after a certain point called as avalanche breakdown VA, the current will increase steeply. Now this current will increase more steeply than this. So what happens here is, if you observe this region, current is increasing by infinity. It's almost infinite, right? While there is a very small difference in voltage here. So the difference in voltage is small while current is increasing infinite times, which means even if you change the voltage a bit, the current increases steeply, and this causes heating in a diode. To prevent this, we use a Zener diode, which is used to handle this region so that it can operate in this region. So that is why we need a Zener diode over a normal diode. A normal diode would burn out in this region, because even with a small change in voltage the current increases steeply, and that is why we need a Zener diode. So the IV characteristics of a Zener diode and a normal diode is the same. The only difference is a Zener diode can operate in this region. Now why do we need to use these characteristics? Is because we use a Zener diode as a voltage regulator. So we use Zener diode as a voltage regulator. We know what voltage is, but what is regulation? So suppose I have my voltage which is changing a bit. Suppose this is the waveform of voltage which is changing a bit with time. So in the output I should have a constant voltage supply, which means even if I change the voltage a bit over here, see it is varying, right? It is changing a bit. So even if I change the voltage here, I should not get any difference in power supply. That is what is happening here. even though there is a large change in the value of current, the voltage isn't changing much. Okay, in an ideal diode, the reverse characteristics will be almost a straight line, which means, so in an ideal diode, the characteristics will be almost a straight line, which means no matter how much current you change, the voltage won't change. Okay, so we use this property of a diode to design a voltage regulator. So let us see how a voltage regulator works. So this is how the voltage regulator circuit is. So I have a power supply here, then I have a resistor, then I connect a Zener diode, of course in reverse bias. So this is the positive side. Okay, so to connect it in reverse bias, I need to connect the Zener diode, the positive of Zener diode, to the negative of the circuit. Okay, so here I will have the positive part. Now we know anode is positive and cathode is negative. So this is the anode, let me write it as anode, and this is the cathode. Now the representation of Zener diode is different. If it is a Zener diode, you need to mention this as well, because only then it can handle the reverse current. And this is the cathode. So the symbol is almost the same, the only difference is these two. Okay, and then in parallel I will connect a load resistor, RL. Clear with the circuit? Okay, so now what happens is, as you can see, I have a voltage source over here such that the Zener diode is in reverse bias. Okay, so when a Zener diode is in reverse bias, we'll get these characteristics. Okay, so I will try to maintain the voltage at some point, let us call it as 6.7 volts, which would be the avalanche breakdown of the Zener diode, VA, 6.7 volts. Okay, one more thing, don't get confused between avalanche and breakdown voltage. Avalanche is when it is in the reverse bias, and breakdown is when it is in the forward bias. Okay, suppose the Zener diode is receiving 6.7 volts. What does that mean is, now as you can see, this diode and load resistor are in parallel, which means if there is 6.7 volts across the diode, there will be 6.7 volt across the load resistance as well. Okay, now suppose I increase the current delivered by this source, what happens is this. So current is increasing. Suppose first it was minus 20, now it is minus 40, for example. Now observe the change in voltage over that period. So I have increased this from 20 to 40. How much does voltage change? If it is an ideal diode, then it will not change at all. Okay, so this 6.7 volts will be maintained across Zener diode, and since this is in parallel with this, we'll get 6.7 volts again at the load resistance. So what we see here is, no matter how much current is delivered by this voltage source, the output voltage across RL is maintained at 6.7 volts. But for that we need to operate the Zener diode in this region where the voltage is barely increasing with current. Okay, so that's it about Zener diodes and its application as a voltage regulator.